Hi, welcome back to Statistics. My name is Mrs. Puentes. We're almost through the semester. We probably only have about five more weeks. So today we are going to discuss Chapter 10, which is hypothesis testing. And this is real statistics. This hypothesis testing is what psychologists do, what the FDA does to improve medications, and more importantly, in business applications, how do they launch a product? Or how do you know that a new machine has increased production statistically? So we do that by a 5-step process called hypothesis testing. What I'm going to do is I'm going to be pretty consistent with the book's 5 steps to help make it a little bit easier for you. But in the test or in your notes or even in the problems you do, if you don't do the 5 steps exactly like in the book, that's fine, as long as you include the 5 steps. Okay, each of the steps are important, and we'll go over the 5 steps. We're going to go over the 5 steps when we use mean data for Z, for T, for proportion data. And then I'm also going to discuss Chapter 11 briefly, is when we are comparing to proportion. So what I'd first like to do is discuss a little bit of hypothesis testing. So I hope you printed out Chapter 10 handout. There is a picture of Chapter 10 handout for your review. And I want you to note the first step, hypothesis testing. What we are going to do in this chapter is we are going to take, let's say, a product like pencils. We make 1,000 pencils. For years and years and years, we make 1,000 pencils a day, okay? And we know the standard deviation is, let's say, 15. Because some days we make 950, some days we make 1,050, some days we make 1,002. There's some variation, okay? But we know what that standard deviation. Well, I grab a sample of, let's say, 50, after I put in a brand new process, and during that new process, I grab a sample size of 50, and I find that the sample average is now 1,100. So this is the population mean, which is mu. This is the sample mean. And most importantly, this is the population standard deviation, sigma. This, because I have the population standard deviation, it's a Z. We're going to use the Z table. Now, what we are going to test is, are we statistically making more pencils every day? Or is this just randomness? Because sometimes we make more and sometimes we make less. That's what we're going to do. Now, sometimes we have a population standard deviation. Sometimes we have a population mean. Let's say now we're producing pens, and we make 500 pens in our population. We implement a new process and we sample 50 of these, and we get a sample mean of 510. But we don't have the population standard deviation of this. We have a sample standard deviation of 5. Because we have a sample standard deviation, we always use the T statistic. Okay? So let's continue with that thought. Our first step is to write the null and alternate. Null is h sub 0, alternate is h sub 1. Okay? Right here. In order to write the null and alternate hypothesis, you have to look for keywords in the question. And we're going to go through a question and I'm going to point out keywords. However, if we use a word like different, or equal, or not equal, or change, we are going to use equal and not equal in our null and alternate hypothesis. So if we use keywords like change or different in our question, it's going to be equal and not equal. And by the way, that is a two-tail. If I use words like greater than, greater, or faster, or more than, I'm going to use the greater than sign in the alternate. And if I have a greater than sign here, I'm going to have a less than or equal as the null. Has to be in this combination. If I say slower, less, smaller, fewer, I am going to write the less than sign for the alternate and then the greater than equal sign for the null. These are the only three combinations you will ever have in a null and alternate hypothesis. This 200, I just used a number. Each one of these examples we're going to have a different. We're testing a population. This population happened to have 200 desks. But that number could change. Okay? That's the first step, to identify which of these null and alternate hypotheses you're going to use. The second step is this is the easiest question I'm ever going to give you in the entire semester. You pull it right from the problem. It's the alpha. Is it 0.05, 0.10, or 0.1? That's all you have to write down. Okay? Each of these will help you identify what your critical value or your decision rule is, and we'll go over that in a few minutes. Again, your third step is to determine whether it's a Z or a T statistic. If it's a Z statistic and it's mean data, you're going to use this formula. If we determine, as I mentioned before, if we have our sample standard deviation, it's going to be a T statistic. See, this is the sample standard deviation, and this is the population. They're essentially the same formula, which is fine. However, when we look them up in the table, this one will have to use the T table, and this one the T table. Our last concept we're going to go over is when I have proportion data, and that uses a different formula, which is make sure you put parentheses. Now, all three of these formulas are located in the table I've given you. That chart. Remember the chart I gave you a few weeks ago? Let's see if I can find one here for you. I can't find one right now, but when I do come across it, these are the three formulas you will use in your hypothesis testing. Right now, it's either Z or T. Step 4. We are going to draw the curve, and we are going to identify the rejection or the do not rejection area from the critical value. The book calls it the decision rule or the critical value. Step 5 is we're going to use one of these formulas in a calculation, and then we're going to plot it on this curve that we've drawn. Okay? So the table, the formula I was talking about, you will find all three of these formulas right here on your chart. And if you notice here, it's the third one, I identify these as hypothesis testing. It's the Z, the T, or the proportion one. Okay, let's go to our first problem. Example. Company manufactures and assembles desks. The weekly production of desks follows a normal probability distribution with a mean of 200, standard deviation of 16. A recent new production method has been introduced, and the sample production mean is 203.5 per weeks for 50 weeks. The vice president of manufacturing would like to investigate whether there's been a change in the weekly production of desks at the 0.01 significance level. Okay. First thing you need to do this is write the givens. So I am going to write the givens for you. Givens. The population mean, for years and years we've been making 200. This standard deviation is the population because I haven't mentioned anything yet about sampling. I did sample, put in a new production method, and I sampled 50 weeks, and now we're up to 203.5 desks. Well, I'm trying to decide, are these two statistically different, or are they statistically the same at the 0.01 level? That's my givens. Very important. Because of this population standard deviation, this tells me it's going to be a Z statistic, and I'm going to use that Z formula. Okay, step one, null and alternate hypothesis. Typically, we write the alternate first. We want to know if the population mean, and we have to find the key word in the question. It's typically right in the question, and I have actually highlighted the keyword change. The word change is equal and not equal. And we always put the population right here. So we want to know, has the population changed from 200? Step 2, alpha is 0.01. 3, which of these formulas? Because I have the population standard deviation, I just want you to write the formula here. Like I said, if you mess up these steps or combine these steps, I'm not going to worry about it as long as the information's there. Step 4 is to draw the curve with the critical values. Well, the first thing you want to know, this identifies whether it's one or two tail. If you look up here, equal and not equal is always a two tail. So we have a tail here and a tail here. Well, what is the decision rule or the critical value here? Okay. What is it? We can look at, since it's Z, it's a two tail at 0.01, so it's 2.575. Negative 2.575 and a positive 2.575. That's my critical value. When I do my calculation now from my sample, if I fall in between here, I do not reject the null hypothesis. If I fall above 2.575, I reject it. And if I fall below it, I reject my null hypothesis. So let's do the calculation. Do it. Z, 2 minus 200. 203.5 minus 200. Make sure you put parentheses around that, please. divided by 16 over the square root of 50. You might want to throw parentheses there. My calculated z is 1.55. That is below here. It's right here, 1.55. Part of the answer, you need to write, do not reject null hypothesis. And what I tell students to do, here's the null hypothesis, right? I'm not rejecting it. Box it and put these symbols back into words. The mean equals 200. So in other words, the new production method equals 200 desks per week. So we have not increased our production. These two are not statistically different. So what do? We fire the production manager that implemented the new process. After all that time and money spent, we're still making the same number of desks. This is how they evaluate a new process or a new product, or whether they test market a new product and whether they should introduce it by hypothesis testing. Okay? Now I'm not going to do the next problem. The next problem is exactly the same, except it has a different key word, and we use more than. So I'm just going to write the null and alternate hypothesis. Your critical values will change. It'll be a one tail. Your null hypothesis, your alternate hypothesis. More than. More than, the sign for more than is a greater than. 200. Then your null hypothesis always goes in the other direction and always has an equal sign. So that would be the null and alternate hypothesis, or step one for the next problem. I want to remember, equal sign is part of the null hypothesis. So that's an example with the T example. You can put it on pause now and try the next problem, next couple of problems, and then come back to me because I want to do this T example. So the T example. Let's write, I want you to pause it and write down the givens. You should be getting good at the givens. Okay, let's look at the givens. We have, it costs $60 to process a claim. Years and years, we know that. Okay, we sampled 26 claims. We looked, and on my PowerPoint, you'll see those 26 claims. And from there, I used my statistical calculator, and I found a mean to process it after we changed the processing system. It only cost $56.42, and the sample standard deviation was $10.04. Well, since we have a sample standard deviation, that tells me it's a t distribution, not a z, because I have a sample standard deviation. Now, we want to test to see if these are statistically different. What is the key word? Now less than. So our first step, null and alternate hypothesis. Less than sign. There's your less than sign. If it's less than, then our alternate has equal and 60. Okay? 2, alpha equals 0.01. Significance level. 3, I've already told you it's a t distribution. There's the formula we'll use. 4, I want to draw the curve. Is this a 1 or 2 tail? It's a 1 tail. And here's a little secret. How do you know it's a 1 tail because it's not equal sign. But how do you know which side to draw the tail on? The alternate points to the left, the tail is to the left. If the alternate points to the left, the tail's on the left. So let's go to the t-table. The t-table, you need two pieces of information. Actually, three. You need the degrees of freedom, which is 25. You need one or two tail, it's a one tail, and you need 0.01. So 25 degrees of freedom, 25 degrees of freedom, one tail 0.01, come up here, 2.485. 25 degrees of freedom, one tail, 0.01, 2.485. And because it's on the left side, negative 2.485. When we, in the fifth step, we do our calculation, which is 56.42 minus 60 over the standard deviation of 10.04, square root of 26. Make sure this is in parentheses, and we get a negative 1.8. Negative 1.8. This is in the do not reject the null hypothesis. So we don't reject it. I'm going to box it. We're not going to reject it. So therefore, the mean is greater than and equal to 60. So we did not reduce the processing time for the claims. It's greater than or equal to 60. We fire a second person after they implemented this new cost-cutting measures. Okay? That's a t-statistic. You can pause it again and do the fuse example. And now I'm going to do a proportion example. Proportion. I'm going to let you read this. What's our givens? We have the population percent is 80. By the way, in the book, the symbol is pi. I think I told you that before, but I just want to remind you. We found out, we sampled 2,000 people, and we found that 1,550 will vote for the incumbent. Well, from this information, you calculate the sample proportion. 1,500 over 2,000 is 0.775. Well, are these statistically the same and he's going to win the election? Or are they statistically different and they're not? So you always have to calculate the sample proportion. Okay? When you read a problem, you might say, oh, how do I know if it's a proportion or a mean or a T or a Z? Remember, if I give you a percent, it's a proportion. And I did not give you a standard deviation. So that would identify it as a proportion. Okay, so let's write the null and alternate. This one's a little bit tricky. Oh, by the way, instead of using mu, we're going to use population. We're testing the population proportion. It's a little bit difficult in here to find the keyword. See if you can find it. At least 80%. This is one of the very unusual times where you will write the null hypothesis first, 80%. Right there. This is at least 80%. I wrote it. And then the alternate has to go the other way. Second step is alpha is 0.05. This time, guys, we're going to use the z. We always use the z for proportion, but we've got to use the proportion formula. Right there. Step 4, let's draw the curve. Is it one or two tail? It's a one tail, and again, it's pointing in the left direction, so our critical value is here. We look at our critical value for z. Critical value, one tail, 0.05, one tail, 0.05, 1.645, negative 1.645. Okay, I will substitute it in the formula here for you. So the proportion of the sample is 775 minus 80% in parentheses, over the square root of 80% times 1 minus 80% over the sample size of 2,000. Now, if you notice, everything in this, except the sample size, is a percent. Percents will always be between 0 and 1. Do not put 1550 someplace here. This is not a percent. You only have p's here. Those have to be percents. When you do this calculation, you got a negative 2.80, which is here. So this is in the reject the null hypothesis. So we're going to reject it. We're going to box the alternate, and that says the population percent that will vote for him is less than 80%. So the poor guy's not going to win the election. Okay? So I've done a Z example with the desks. I've done a T example with the insurance claims. I've done a proportion example with the voting. And that will be all of that's what you have to know for chapter 10. Now I'm briefly going to talk about chapter 11. And I hope you printed out chapter 11 handout. You can pause this and print out chapter 11. What's different about chapter 11 from the other chapter is in chapter 10, I had a population and I sampled to see if that was true. Okay? And I accepted what the population said or I rejected it. Okay? In chapter 11, we're comparing two populations or two samples. For example, men versus women. Maybe my 10 o'clock class GPA versus my 11 o'clock class GPA. I'm testing two populations to see if they're equal. I might be testing the gas mileage of the Toyota Corolla and the Honda Civic. I'm testing two populations to see if them, or two proportions, maybe the percent of males going to a four-year college and the percent of women going to a four-year college. I'm comparing two. Okay? So let's look at that. We're using different formulas, and we are only going to use two formulas here. We're not even going to use the t-table. When we test means, we are going to test the mean of one minus the mean of another, and then depending on what we have, the population standard deviation divided by sample size plus the population, we're actually squaring it, so it's called the variance of the other. Okay? In this example, I'll give you a minute to read it. We are comparing whether you scan your groceries or I'm sorry, the checkout, there's a checkout person scans your groceries or you scan them yourself. Okay? We have a sample mean to scan was 1.5 and the sample mean when you scan it is 5.3. Sample standard deviation is 0.4. Sample standard deviation is 0.3. And this is the sample size. So two different populations, whether you scan it yourself or you have a checkout person scan it. Okay. Well, let's write our null and alternate. We have to look for a key word. Longer than. So, little bit different notation. We want to know if the standard method longer, greater than the U-scan method. If it's greater than there, it's less than there. Step 2, at the 0.01 level. 3. There's your formula. I'm sorry. I know. I'll give you a minute to catch up with me. I didn't realize it wasn't on the screen. The formula is going to be this formula. There's your null and alternate. I don't know if you saw it. Step 4, we're drawing our curve. It's on the right, one tail on the right side, and our z is 0.23. We're only going to use z for this chapter. Next step, to do our calculation. 5.5 minus 5.3 over 0.4 squared over sample size of 50 plus 0.3 squared over sample size of 100. And when we do this calculation, we get 3.13, which is over here, which is in the reject our null hypothesis. We're going to reject it, so we're going to rewrite that one. The standard method is longer than this U-scan. Standard method longer than U-scan. By the way, you will have to put on your test, reject null hypothesis. That's important. You will get points off. Okay? Give you a minute there. Okay, that's comparing two population means. We're looking at minutes here. By the way, in a problem like this, you don't have to write the given. And this is actually the given right here. This is the given. You don't have to rewrite that. Okay? Now I'm going to give you, I want you to put it on pause and read this proportion one, this percent problem one. Okay? It's talking about perfume. Okay, you're back with me. And I want to, first of all, you have to do some calculations here. Pool the percents. Well, first of all, you're going to calculate the percent that there's two different age groups. There's 19 out of 100 like this perfume, or 19%. And then 62 out of 200 like it, out of this other age group, or 32. So we want to know about those 2%. Are they the same or different? Those two populations of women like this percent. The first calculation, since we're dealing with 2%, two population percents, we have to calculate a pooled percent. And that is just the 19 plus 62, or the total overall percent plus 100 plus 200. So 27% total people like the smell of this perfume. So we calculated the individual percents of the age group and the total percent that liked it. Okay. Let's go and write our null and alternate hypothesis. Keyword, difference. So we want to know if the percent of older women and the percent of younger women are equal or not equal. Equal is always the null hypothesis. Alpha is 0.05. The formula, I'm not going to write the formulas. The formula is right here. Take me too long. That's the formula when we're comparing two population percents. What I will do is draw the curve. Since it's equal and not equal, one or two tail. And if you look it up in the Z table, negative 1.96 and a positive 1.96. This is the do not reject area, null hypothesis. This is the reject the null hypothesis. Okay, now the formula. Okay, the formula. Here we go. We have the individual percents, 19 minus 31. Again, make sure you put that in parentheses. Over P sub C goes in here. That's P sub C, the total percent. So it's 0.27, 1 minus 0.27 over the first sample size, 100, plus 0.27, 1 minus 0.27 over the other sample size of 200. When you do this calculation, you have a negative 2.2. You might want to pause it because I think it's going to take you a minute or two to put that on your calculator. You plot that. Negative 2.2. It's in the rejection. So our conclusion is reject the null hypothesis. Reject this null hypothesis. The percent of old women and young women that like the scent is different. The percents of old and young is different. So what does that mean from a business standpoint? We would market it toward the 32% people. The older women seem to like this scent better. Okay? Those are 5 examples of the problem that you'll be responsible for in chapter 10 and 11. And this is pretty much ends this recording for chapter 10 and 11. And have a good day.